Have you ever wondered what that massive crimson storm swirling on Jupiter actually is, and why it refuses to disappear? Today, we're diving deep into one of the solar system's most captivating mysteries that has puzzled astronomers for centuries and continues to defy our understanding of planetary weather systems. Picture this: a storm so enormous it could swallow Earth 3 times over, spinning relentlessly for hundreds of years without showing any signs of stopping. This isn't science fiction. This is Jupiter's Great Red Spot, and the science behind its existence is absolutely mind-blowing. What makes this celestial phenomenon even more incredible is that while hurricanes on Earth barely last a few weeks, this Jovian giant has been raging since before your great-great-great-grandparents were even born. The question that keeps scientists awake at night is simple yet profound. What kind of forces could possibly sustain such a colossal storm for so long? Let's start by wrapping our heads around just how massive this thing actually is. When we talk about the Great Red Spot, we're not discussing some small weather disturbance. This is a hurricane-like storm that measures roughly 10,000 miles across. That's wider than the entire diameter of our planet, Earth. Imagine looking down at our world from space and then picturing a storm system that could completely engulf it with room to spare. That's the scale we're dealing with here. The storm rotates counterclockwise, completing one full rotation every 6 Earth days. The winds at its edges howl at speeds reaching 400 miles per hour. That's more than twice as fast as the strongest hurricanes ever recorded on our planet. These aren't just impressive numbers on paper. They represent forces of nature that dwarf anything we experience in our terrestrial weather systems. But here's where things get really interesting. Unlike Earth's storms that draw their energy from warm ocean waters and eventually lose steam when they hit land, Jupiter's Great Red Spot exists in a completely different environment. Jupiter doesn't have solid ground or oceans like we do. Instead, it's what scientists call a gas giant, essentially a massive ball of hydrogen and helium with no definitive surface to speak of. The story of how we discovered this remarkable feature takes us back several centuries. The first recorded observations date back to the 1600s, when early astronomers peering through primitive telescopes noticed a peculiar reddish oval shape on Jupiter's surface. Giovanni Cassini, the same astronomer who discovered several of Saturn's moons, was among the first to document this mysterious spot in 1665. However, there's some debate among historians and astronomers about whether these early observations were actually of the same storm we see today. What we do know for certain is that by the 1800s, astronomers were consistently tracking a large red oval on Jupiter that matches the position and characteristics of today's Great Red Spot. The fascinating thing about these historical observations is how they reveal the storm's changing nature over time. Early sketches and descriptions suggest the Great Red Spot was once much larger and more intensely colored than it appears today. Modern measurements indicate it has been gradually shrinking over the past century, though it still remains impressively massive by any earthly standard. Now, let's dig into the meat of our mystery. What exactly causes this storm, and why does it keep going? The answer lies in understanding Jupiter's unique atmospheric conditions and the fundamental differences between weather on a gas giant versus weather on a rocky planet like Earth. Jupiter's atmosphere is a turbulent sea of hydrogen and helium, with trace amounts of methane, ammonia, and other compounds. Unlike Earth's relatively thin atmospheric layer, Jupiter's atmosphere extends deep into the planet, potentially thousands of miles down. This creates a three-dimensional weather system that's far more complex than anything we experience on our home planet. The Great Red Spot is what meteorologists call an anticyclonic storm. This means it rotates in the opposite direction to the planet's rotation, counterclockwise in Jupiter's southern hemisphere. On Earth, anticyclones are typically associated with high-pressure systems and calm weather, but Jupiter plays by completely different rules. The storm's reddish color, which gives it its iconic name, comes from complex chemical reactions happening high in Jupiter's atmosphere. Scientists believe that compounds containing phosphorus, sulfur, or organic molecules get lifted high into the atmosphere, where ultraviolet radiation from the sun triggers chemical changes that produce the distinctive red-brown coloration we observe. One of the key factors that allows the Great Red Spot to persist for so long is Jupiter's lack of continental landmasses. On Earth, hurricanes and typhoons eventually weaken and dissipate when they encounter land because the rough terrain and lack of warm water disrupt their circulation patterns. Jupiter's storms face no such obstacles. They can rage unimpeded through the planet's fluid atmosphere for incredibly long periods. But there's more to the story than just an absence of land. The Great Red Spot's longevity is also tied to its interaction with Jupiter's complex system of jet streams and atmospheric bands. Jupiter's rapid rotation, it completes one full day in less than 10 Earth hours, creates powerful jet streams that flow in alternating directions at different latitudes. These jet streams act like cosmic guardrails, helping to contain and stabilize large storm systems like the Great Red Spot. The storm sits nestled between two of these jet streams, which prevents it from drifting too far north or south and helps maintain its structural integrity over long periods. Another crucial factor is the storm's sheer size and the way it interacts with smaller weather systems. The Great Red Spot doesn't exist in isolation. It's constantly interacting with smaller storms and atmospheric disturbances around it. Sometimes it absorbs these smaller storms, feeding off their energy like a cosmic vacuum cleaner. Other times it deflects them or tears them apart with its powerful circulation. This process of storm interaction is absolutely critical to understanding the Great Red Spot's persistence. Rather than gradually losing energy over time, like earthly storms do, the Great Red Spot can actually gain energy by consuming smaller storms that wander too close. It's like a giant atmospheric predator that feeds on its smaller cousins to maintain its strength. Recent research using computer models and data from space missions has revealed another fascinating aspect of the storm's behavior. Scientists have discovered that the Great Red Spot isn't just a surface phenomenon. It extends deep into Jupiter's atmosphere, possibly reaching depths of several hundred miles below the visible cloud tops. This deep vertical structure helps explain the storm's stability. While surface features might be disrupted by various atmospheric disturbances, the deeper portions of the storm remain more isolated from these surface perturbations. This creates a kind of atmospheric anchor that helps keep the entire system stable over long periods. The heat dynamics of Jupiter also play a crucial role in sustaining the Great Red Spot. Unlike Earth, which receives most of its energy from the sun, Jupiter actually radiates more heat than it receives from solar radiation. This internal heat source comes from the planet's continued gravitational contraction. Jupiter is still slowly shrinking from its formation billions of years ago, and this process generates significant internal heat. This internal heat creates convection currents throughout Jupiter's atmosphere, providing a constant source of energy that can help sustain large storm systems. The Great Red Spot essentially taps into this planetary-scale energy source, which is why it can persist far longer than any storm system powered solely by external heating from the sun. The magnetic field surrounding Jupiter also influences atmospheric behavior in ways that don't occur on Earth. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and this powerful magnetic environment can affect the motion of charged particles in the atmosphere, potentially contributing to the complex dynamics that sustain the Great Red Spot. Space missions have provided increasingly detailed views of this remarkable storm system. The Voyager probes in the late 1970s gave us our first close-up images, revealing the Great Red Spot's intricate internal structure with swirling patterns and smaller vortices embedded within the larger circulation. More recent missions like Juno have provided even more detailed information about the storm's three-dimensional structure and behavior. One of the most intriguing discoveries from these missions is that the Great Red Spot appears to be slowly changing over time. Not only is it shrinking in size, but its color intensity seems to be fluctuating as well. Sometimes it appears as a deep brick red color, while at other times it fades to a pale salmon or even becomes nearly invisible in certain wavelengths of light. These changes suggest that while the storm is remarkably persistent, it's not completely static. The exact mechanisms driving these variations are still being studied, but they likely involve changes in the chemical composition of the storm's upper layers or variations in the vertical mixing of atmospheric materials. The study of Jupiter's Great Red Spot has implications that extend far beyond our solar system. As we discover more exoplanets, planets orbiting other stars, many of them turn out to be gas giants similar to Jupiter. Understanding how atmospheric dynamics work on Jupiter helps U.S. interpret observations of these distant worlds and predict what kinds of weather systems might exist throughout the galaxy. Climate modeling techniques developed to study Jupiter's atmosphere have also contributed to our understanding of complex weather systems here on Earth. The mathematical tools and computer simulations used to model the Great Red Spot's behavior have applications in studying terrestrial hurricanes, typhoons, and other large-scale weather phenomena. Looking toward the future, several upcoming space missions will continue to study Jupiter and its fascinating weather systems. These missions will use increasingly sophisticated instruments to probe deeper into the planet's atmosphere and provide more detailed information about how storms like the Great Red Spot form, evolve, and persist over such long timescales. The Great Red Spot also serves as a natural laboratory for studying fluid dynamics under extreme conditions. The physics governing the storm's behavior involve complex interactions between rotation, convection, magnetic fields, and chemical processes that would be impossible to recreate in any earthly laboratory. By studying this natural phenomenon, scientists gain insights into fundamental physical processes that apply throughout the universe. As we wrap up our exploration of this cosmic hurricane, it's worth reflecting on what the Great Red Spot represents in the broader context of planetary science. This storm system demonstrates the incredible diversity of weather patterns that exist throughout our solar system and reminds us that Earth's relatively calm and stable climate is actually quite unusual when viewed from a cosmic perspective. The Great Red Spot stands as a testament to the dynamic and ever-changing nature of planetary atmospheres. While it has persisted for centuries, ongoing observations show that it continues to evolve and change, providing new mysteries for future generations of scientists to unravel. In conclusion, Jupiter's Great Red Spot exists due to a perfect storm of conditions, literally and figuratively. Its formation and persistence result from Jupiter's unique characteristics as a gas giant: the lack of solid surfaces to disrupt atmospheric flow, powerful jet streams that help contain and stabilize the storm, the planet's rapid rotation creating complex atmospheric dynamics, internal heat sources providing sustained energy, and the storm's ability to feed on smaller atmospheric disturbances. The combination of these factors creates an environment where a storm system can not only form, but persist for hundreds of years, making it one of the most enduring and spectacular weather phenomena in our entire solar system. This remarkable storm continues to challenge our understanding of planetary atmospheres while inspiring future exploration and research that will undoubtedly reveal even more secrets about this magnificent cosmic tempest.